All right, welcome back, everyone. Looks like the class is getting smaller and smaller. So we've been talking about first-order approximations of different functions. First, we looked at scalar input functions. And in this case, maybe we have a function like this. We have a reference point W naught, and we want to get the best linear approximation of that function at that reference point. And for this, basically, we can use the Taylor series, and we just truncate the first two terms. And all the higher order terms, we essentially, in the approximation, we drop them. But then sometimes if we want to talk about the exact function, then rather than giving all the details of all the different higher order terms, we summarize them as this big O term. And the big O means that all that stuff together is at most a constant times whatever is in the big O, in this case, W minus W naught squared, whenever this quantity here is close to zero. So we saw this first for scalar input functions. Then we repeated it for vector input functions. And the only thing that changed was when we do the Taylor series approximation, we have a sum of these scalar derivatives here. And the big O term involves the norm between W, the vector, and its reference point. And we saw that we can write that middle term as the inner product between the gradient and the deviation from the reference. And then we used that to prove a couple things about the gradient that we said earlier, which is that the gradient tells us both the direction of maximum increase at a given point, as well as the slope of that increase. And we did that by looking at this directional derivative, plugging in the Taylor series, taking epsilon to zero, at which point we found that this big O term essentially vanishes. And then we were able to find that this directional derivative is the norm of the gradient times some quantity between 1 and minus 1. And when we look at the direction u that is in line with the gradient, we get the largest version of this, which is 1, which tells us that if we want to move in the steepest uphill direction, we should go in basically the negative gradient direction, actually the gradient direction. And then this ends up being the slope itself, the norm of the gradient. So the gradient tells us both the maximum slope and the direction. And then we repeated this for matrix input functions. And so here, when we do the Taylor series, that first term is a double sum over scalar derivatives of the cost with respect to each of the entries in that matrix. And we found that we can also write this in terms of the inner product between the gradient and the deviation. So this is sort of a universal way to look at that middle term. What changes is the definition of the inner product as you go from vectors to matrices. So here the inner product between matrices A and B is the trace of A transpose B. Or equivalently, if you do a pointwise multiply of A and B and you sum up all the terms, that's another way to think about the trace. And yet another way is if you take the entries in A and B and you rasterize them into a big long vector, and then you do the inner product the same way you do with vectors, you get exactly the same thing. So different ways to think about this inner product between matrices. Okay, so that brings us to looking at an example of this first order approximation of matrix input functions. Are there any questions? Yes.
So what do you mean by the linear approximation of the function at the point W naught?
What do I mean? Well, so let's talk about the definition of linearity. So when we say that a function f is linear, it means if you take a scalar, let's say a scalar combination of two inputs. Okay, so here I'm talking about matrix input F. So we have two different matrices, W1 and W2. We have two different scalars, alpha 1 and alpha 2. If F is linear, that means for all alphas and W's, you can get this relation. So this is sort of the definition of linearity, that you can do this linear combination at the input to the function. That's the same as doing it at the output of the function. And so that is true of, actually it's true of this term. This term you could say is an offset. So let's look back at this picture over here. It gives us some insight. So technically speaking, this term is linear. But this term, let me see, is that true? So there's this technicality when there's this offset. So like in terms of this picture, if this is the origin, then a linear function has to go through the origin. But this is not going through the origin because of this intercept. So it's called affine linear. But still, people talk about this as a linear approximation.
So we are approximating the cost function linearly at the point W0.
Yes, you pick a reference, in this case W naught, and then you say essentially what's the best linear approximation of the cost at that point. So when you're exactly at that point, it's perfect. No error in the approximation. You can see that because this goes to 0, all these go to 0, and so then this is true. And then as you move away from it, the error is small. So this is a linear approximation, and the error is at most a constant times a quadratic. But because if this thing is small, when you square it, it gets much smaller. And this is the approximation error. So you're guaranteed that the approximation error is small in this range. As you start getting far away from the reference point, you can see the approximation error can be quite bad. So really the linear approximation is good when you're close to the reference, perfect when you're at the reference, but maybe very bad when you're away from it. Yeah.
So it's just a tangent line to the point that we're looking for?
Yeah, in the one-dimensional case, that's exactly what it is. It's a tangent line. Yes, the slope matches perfectly at that point. Yep. And then when we go to vector input functions, we would just have to try to imagine that not in one dimension, but in like several dimensions. So I guess in that case, you have a picture a little bit more like this. This would be the two-dimensional picture. Higher dimensions becomes difficult to visualize.
So what does W0 denote here?
W0 is just a reference that we choose depending on what we want to do with this linear approximation. So when we did this, we chose the linear approximation. We basically just fixed a point, W0, any point, and then we said, let's move away from that point. And so when we used the Taylor series, W0 was the point we start at, and then the W, which is the points away from the reference, we're just moving in the direction of U.
Are these beta coefficients? Are these the beta coefficients?
The beta coefficient?
I mean, the weights for the model.
No, we don't really have a model here. Like on this page, we're just saying we have a function. Our goal was to convince ourselves that if I'm at a point in the input space and I want to know which direction do I travel in to get the steepest increase, I should go in the gradient direction. So really there's no loss. I mean, you can think of j as an arbitrary function. It could be a loss.
Yeah, I thought it was a loss function.
It could be a loss, but in some other sense, like this is generic. This could be in a math class, not a machine learning class, right? We're just saying there exists some multi-input function j, and the gradient has these properties.
Please remind me, what is the point of the whole term?
The big O is a way of bounding the error. So the true Taylor series has an infinite number of terms. We want to approximate it by only the first two. Therefore, the approximation error is all these other ones. But we want to upper bound the approximation error. And so this tells us that we have a quadratic upper bound. So this says that error is at most a constant times this. Some constant c times that squared difference.
Yeah, because I thought the value and the slope itself can determine just the slope, a line.
Yeah, so the big O term is upper bounding this difference,
Oh,
the approximation error.
okay.
So we're basically saying that error is upper bounded by a quadratic. The intuition behind that is that here's the quadratic term, right? And then over here we have a cubic term. That's the next term in the Taylor series. But if this is a small number, then the square of it is actually bigger than the cube of it, right? So this gives you intuition as to why this is a quadratic upper bound, because the quadratic term dominates the cubic term, and that dominates the fourth power term, and so on and so on. So this is actually the biggest term in the whole expansion. That's why we have a quadratic upper bound and not some other higher power. Okay, great, good questions. Any other questions? Okay, excellent. So we have our different ways of doing the approximations, and now let's do an example of this first order approximation of matrix input functions. So it's kind of a contrived example, but it allows us to do a little bit of linear algebra as well. So this is going to be the function we're going to look at. So this is a function, as you can see, it's a function of a matrix W, and it's scalar output. Everything we're doing here, J has to have a scalar output, but the input is a matrix W. And so this is how we take that matrix and turn it into a scalar. There's some fixed vectors, A and B, which we surround the matrix with to bring it down to a scalar. So we would like to work with our gradient, and we're not used to doing matrix vector valued calculus. So we want to describe things in terms of sums of scalars, where calculus is more familiar to us, where we can just take scalar derivatives. So that's the first step in a lot of these problems. So we would like to rewrite this in terms of summations of scalar terms. So let's say that I'm going to use, as an index over the B terms, I'm going to use K. And as an index over the A terms, I'm going to use J. So how can I write this as a double sum over J and K of some other stuff? So let me ask this to Ji Yao Yuan. Here? No? What about Zhengwan Yun? Zhengwan Yun? Yeah, okay. So how can I write this? This is sort of a question from Unit 1. How do I write this in terms of a double sum? So it's going to involve AJ and BK. You see how to do that? Okay. And what's in the middle? WJK. Exactly. So this is how we can write it. And the reason we're doing this again is we're now exposing these scalar entries, And now we can go back to the definition. What is the j prime k prime entry of the gradient? It's just going to be the derivative with respect to w j prime k prime of this cost, j matrix w. And so now that we've written the cost this way, it should be relatively straightforward to see how to compute this scalar derivative. So let me ask, is Chiping Zhu, Z-H-O-U here? Yeah. Exactly. So it's AJ prime, BK prime. So hopefully everyone sees that. So we're just taking the derivative. Now, the sums disappear because there's only one combination of j and k in the sums that matches this j prime k prime. All the other ones, basically this, all the other ones go away. It's only the j prime k prime entry in the sum that remains, and then when we take the derivative, we just get this times this. Any questions on that? Okay, so next question is, this is the scalar viewpoint. How do I bring that back to the world of matrices? How do I write the entire gradient matrix? So let me see if, is Andrew Lin here? Yeah, so do you see how I can write, based on this expression, how can I write this entire gradient matrix? So we want to have a matrix where j prime is coming down this way, k prime is going across that way, and these are the entries as a function of j prime and k prime. Okay, so maybe it's a little tricky, but the answer looks very simple. It's simply going to be the A vector times the B vector transpose. And maybe it's easier to go backwards. If I give you this and I say, what's the j prime row of that? That's going to involve only aj prime. And if I say, what's the k prime column? That's only going to involve bk prime, and so you get this. Okay, so this is what we call an outer product. It's that A times B transpose, and that gives us this entire matrix, which is the gradient matrix. Is that part clear? Making sense? Okay. So here's our linear approximation. So this is from the previous page. We know we take the cost at the reference, or j at the reference, and then we have the inner product between the gradient matrix transpose the deviation between W and the reference. So now that we know the gradient here, we can just plug that in. So we have the gradient transposed. So if we transpose A times B transpose, we know that we swap the order and we transpose them individually, which gives B A transpose. And now we can use this fun property of the trace, where the trace of a product of matrices B and A, you can actually swap the matrices and you get the same value in the trace. So we can actually swap B and this other stuff by bringing B to this side, at which point we get this. So we started with a matrix inside the trace, but what about this term? What's the shape of this term? It's like a row times a matrix times a column. So what shape is that? Scalar, right? So this is just a scalar. And so if I have the trace of a scalar, then the trace is not really doing anything. It's like you have, scalar's like a 1-by-1 matrix. You're summing the diagonals of a 1-by-1 matrix. That's just the entry you have. So we can get rid of the trace. And then we do one final simplification. We notice that this term gets canceled by this term, and we're back to this. So now you might say, well, this is kind of strange. So we started with J of W. We approximated it with this linear approximation, and then we simplified it, and we got the original J. So that makes sense. If J is linear to start with, then the approximation is perfect. And that's why we got the same answer. So even though it looks like an approximation, for this particular function, it's a perfect approximation. It's actually an inequality. Okay, but this is like typical kind of matrix vector gymnastics that you see in a lot of problems, and typical things with the trace that you tend to see as well. All right, so any questions on this? Okay, great. So let's also look at what happens in Python. So we just want to program this in Python, so we have this function. So one question is, how do we code this in NumPy? There's a couple options. One option is to use this dot operator for matrix vector multiplication. That gives you W times B, and then over here, this is how you do like the A transpose. There's another option. You can use this @ sign, which is like matrix multiplication in NumPy. And so you can do A transpose and then matrix multiplication W, matrix multiplication B. Now, when we come to the gradient, it's a little bit more complicated because in this function, A and B, these guys are 1D arrays. And different from MATLAB, in NumPy, when you have a 1D array, it's neither a row nor a column matrix, because to think about a row vector or a column vector, you really have to be thinking about a matrix. So a row vector would be like a matrix with one row, column vector would be like a matrix with one column. But if I just give you a one-dimensional array, it's not even living in the world of matrices, so it's neither a row nor a column. So if I want to do something like this in NumPy with one-dimensional arrays, I can't. It's not exactly clear how to do it. So this is. So you could do it by programming like a for loop, or actually, like two nested for loops. You could go over all the indices to compute the values. You could compute it like this, but that would be very slow. And so a better option is to use Python broadcasting. So for this, this is what it looks like over here. And so this is what's happening. You can think of this as like saying, I start with a 1D array. I want that to go down the rows of some matrix. And as for the columns of the matrix, I'm just going to copy that same first column over and over again, as many times as are needed for the remainder of the operation. Okay. So again, this is taking a 1D array and making it look like a 2D array by just copying those rows, that first column like this. And then this is doing similar, but this is saying start with a 1D array, use that along the columns, and then make as many new rows as we want. That's what's happening here. And then this is a scalar multiply. Okay, so let me give you another example of this that I stole from the NumPy documentation, which is doing the same thing, but slightly different in that we're looking at addition. So here, what we have is we have a vector A that we want to think of as a column vector. We have a vector B that we want to think of here as a row vector. And essentially what we want to do is we want to get all combinations of elements of A plus elements of B. So we can do that by sort of stretching A into this matrix by copying that over and over, stretching B into the matrix by copying it like this, and then just doing an element-wise addition, which gives us this. So in the code above, it's exactly this, but we're using a multiplication instead of a sum. But this sort of shows what's happening in between. So again, this A colon comma none is going to be an M by something matrix. B none comma colon is a something by n matrix. And NumPy is smart enough to adjust that inner dimension as needed to make this work. So it's kind of a cool thing. Once you get used to it, it's pretty natural. It might look strange at first. Yes?
So that operation gives you the gradient?
Yeah, so this is basically how you want to do this. So again, sort of maybe to say it quicker, you want to do this, but A is 1D array, B is 1D array. So it's sort of like you want to make A into a column vector, right? And so you can think of this as making A into a column vector if you like. And then you can think, I want to make B into a row vector. This is kind of like making B into a row vector, more or less. So again, it's not exactly that. I think it's more clearly explained by what's happening down here. But for the purpose of this example, that's essentially doing that. Okay. Yeah, so NumPy broadcasting again, you can read about it. You'll get some practice in the lab for Unit 6. Okay, any questions on this NumPy implementation? Okay, excellent. So we finished sort of the background material of this unit. We're ready to actually do something useful with all this stuff, which is going to be the gradient descent algorithm. It's actually going to be the prototype method for which we can minimize any cost function, at least any differentiable cost function. So maybe just a little bit more background to see what we can expect to happen. Let's think back to a method we have been using since the beginning of this term, which whenever we want to minimize a function, we've been saying, well, we know that at the minimum of that function, the gradient is 0. So to find that minimizing value, w, let's just search for the w which makes the gradient 0, and then, if everything works out, that would be the minimum. But now it's time to zoom out a little bit and say, it's not that simple. Here's an example of a function which has a minimum over here, and you can see, yes, the slope at that minimum is in fact 0, but it also has a maximum, and you can see that the slope at the maximum is also 0. So when you say, I'll just find the location where I get 0 gradient or 0 derivative, you don't actually know whether you're going to get a minimum or a maximum. You could get either. And the situation is even a little bit more complicated than that. You could also get something called a saddle point. There's different ways to visualize saddle points. If we want to visualize a saddle point in one dimension, we could have something like this. Imagine that this is like, kind of like a cosine, sort of like a cosine that is flipped and shifted down. And then let's say I have a mirror image of that same function like this. Well, when you look right at the origin, the slope is actually 0 there. So that means that if you were here looking for a location of 0 slope, you would actually find that point too. And that's neither a minimum nor a maximum, right? It's a saddle. So there's really a few things that can happen. Saddle points are also interesting in multiple dimensions, like in 2 dimensions. We have 2 dimensions to optimize. A saddle point could be a maximum along this dimension and a minimum along that dimension. So it can sort of simultaneously be kind of like a min and kind of like a max. But then there's other weirder things, other weirder kind of saddles, where in some directions, well, so along this direction, it's a little bit more like what I showed you up here. So there's all kinds of weird things that can happen with saddle points. So the point of all this is to say we have to be careful when we just set derivatives to 0 we could get minima, we could get maxima, we could get saddles. And these locations where the derivative goes to 0 are called stationary points. So there's 3 kinds of stationary points you can have. Okay, any questions? Okay, it's even a little bit worse. So here's an example which shows a function with 2 different minima. And here you can see, yes, the gradient is 0 at each minima, but this minima is lower than this minima. If you really want to minimize this function, this is where you want to be. You don't want to be here. So that means that if you just search for a location where the gradient is 0, you could find a minimum that's not the global minimum. It's this local minimum. So that's another thing that can happen that in many cases we would like to avoid if possible. And the solution to these issues, as we'll talk about at the very end of this unit, is that when you have a special class of function called a convex function, then any local minima is also a global minima. And so you don't have the situation where you have different kinds of minima. They're all sort of equally good. And for these functions, you can simply find a local minima, and then you're content to know that's also the global. Okay. So we'll talk more about these towards the end of the unit. Just wanted to sort of mention that there is sort of a way around this problem for now. Now, unfortunately, in machine learning, it turns out that most interesting losses, so some of the losses we've seen, like RSS, that's convex, like cross entropy, that's also convex. But once we start to get into neural networks and stuff, we no longer have convex losses. And so we do have these issues of global and local minima, and that's the situation in practical machine learning, at least modern machine learning. Okay, so we'll get back to that in a moment, but for now, recognize that there's different kinds of minima. All right, any questions on this? Okay, so finally, let's talk about the gradient descent algorithm. Okay, so our objective since the beginning of this unit is we're given a loss function j that's a function of some parameters w. Our objective is to find the minimizing set of parameters w. And for the moment, we are just going to have to settle for a local minimum. In other words, if there's global and local, this gradient descent procedure may converge to a local minima. There's no way to guarantee that it's going to converge to global if the function is not convex. Okay, so this is what we want to do, is we want to find a local minimizer of this function. This function will often refer to it as the loss or the cost or the objective. One thing to note is that we are not imposing any constraints on W. We're not saying, like, for example, the coefficients need to be positive or they need to be within some range. So right now, this is the simplest case where we say the optimization is unconstrained, no constraints on W. We will talk about constrained optimization later. Also, we will assume that we can compute gradients. For this, we need that the function is differentiable. If we can't compute gradients, what we're describing here, gradient descent, doesn't work. So these are a few sort of caveats. But finally, this is the approach. So if I want to describe the approach in words, we start somewhere with a guess of the solution, maybe a very bad guess, and we just take downhill steps down this loss, small downhill steps until we stop. And as we know, the gradient points in the maximum uphill direction, so we just want to move in the negative gradient direction every time we take a step. But notice what can happen if I take a very large step. Maybe I start here, and I take a large step, and I end up over here. Now I'm actually worse than where I started off with, right? So that's why it's essential to take small steps. If I take a small enough step, as we'll prove in the next page or so, if I take a small enough step, I'm guaranteed to make progress. Downhill, downhill, downhill. And eventually, I'll get to the bottom, or at least the closest minima to where I start, the local minima. So that's the idea in words. And if we want to write this down in equations, we could do it like this. We're going to use the superscript to denote the iteration k. So w at the k plus 1th iteration is going to be w at the kth iteration minus some small step size alpha k times the gradient evaluated at the current guess wk. Okay, so compute gradient at the current guess. Now look at the negative gradient, that's the downhill direction. Multiply it by a small positive number. And that is how far you move from your current guess. That becomes your new guess. So you start at W0, then small downhill step, W1, and so on. Notice that you're not necessarily moving in the best direction. So here, the gradient is not pointing you directly towards the solution. It's pointing you somewhere else, right? It's important to realize gradient descent does not take the straightest path to the solution. In fact, more and more this is stretched. The worse and worse gradient descent takes you in the wrong direction. If these contours are circular, then you go right to the center. But this is the main weakness of gradient descent, is that when the cost surface is very stretched, you end up moving kind of almost orthogonal to the direction you would like to move in at the beginning, and eventually, when you get towards the end, that's when you start curving and actually moving in the right direction. Okay. All right, so that's a lot of ideas on this slide, very important ones. Are there any questions here about the approach? Yeah.
It says take small down steps until you reach the bottom. What is the representation of that bottom? Like, what is the bottom? Why is it?
So these are the cost contours, equal cost contours. So this is like high cost, lower, 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 lower. So here, we hope that this is the local minimum, the bottom of the bowl.
Okay.
Yeah.
So that's the global minimum?
No. So let's say we were doing gradient descent here in one dimension. Let's say we started over here. So I would go so here I can only travel left or right. So I want to travel in the negative gradient direction. You can see the gradient says move left. So I would start here, I'd move and eventually I'd come here and I would stop. Right? So I would not converge over here. Unfortunately. Might like to converge over there, but I won't. Gradient descent doesn't do that for me.
So why wouldn't you just find all the minima in the function and then just choose the lowest?
That's a great question. In one dimensions, you can do that. So like you could make a grid of points and you could evaluate them without maybe very much computational complexity. Think about what happens now in 2 dimensions. The number of points is squared, right? You have a 2-dimensional grid. That's a lot more points. Now 3 dimensions. You have a cubical volume. You have this 3-dimensional grid. That's a lot more points. So as the dimensionality of your W vector goes up, this grid search problem grows exponentially in complexity. And so that's why in practice, we can't do grid searches in high dimensional spaces. Yeah. So instead, we just basically try to go downhill, downhill, downhill. And for us, the computational complexity of this really boils down to how much effort is it to compute that gradient. And we'll get into a lot of details there, especially when we start talking about neural networks. We'll show that there's this really nice backpropagation algorithm that allows us to compute this gradient very efficiently, even in networks that have billions of parameters. Yeah. Okay, but that's a great question. All right. Any other questions about gradient descent, what we're doing, why we're doing it? Okay, excellent. So let's now convince ourselves that this actually works. So for this, we're going to come back to our Taylor series expansion that we developed earlier. So if you remember what that is, our reference point now, we're going to choose it as W at the kth iteration. So this is just another example. Whenever we apply the Taylor series approximation, it's, we're choosing the reference in a way that is productive for us in the analysis we're doing. So here the reference is W at the kth step. And that's the first term, the constant term. Then we have the gradient, also evaluated at WK, transpose W minus the reference, plus the big O term, which gives us an upper bound on all those other terms in the Taylor series. Okay. Now we would like to know, we're starting at one point and we're moving to the next point. We want to know, at the end of the day, we want to know, is the next point a lower cost than the original point? If we've decreased the cost, we've made progress. If we've increased the cost, we're actually going in the opposite direction. So the W we're going to look at now is the specific point, which is the next point. So we have the original point here, the next point here. And all I have to do is just replace this W with WK plus 1 with the same expression. Okay. So now, if we're using the gradient descent algorithm, we actually know exactly what this difference is. If you look back to the previous page and you bring this WK to the other side, you see that this is actually the difference between WK plus 1 and WK. So we can just substitute that expression minus alpha k times the gradient at WK. We can simply substitute this expression for this and this. And once we do that, okay, if I plug this into here, then you can see I have gradient transpose times gradient. So that is the norm of the gradient squared. And then over here, I'm just plugging this in here. And the negative sign is not really important. Inside this norm, the negative won't affect things, so we can drop it. And we can pull out this scalar alpha k out of the norm and square it. So that's what's happened over here. And now, what's interesting is you see we have a norm of gradient squared. We have another norm of gradient squared. Okay, so we need to just be a little bit more precise now. So this big O term, we know that this means there exists some constant, which we call capital C, which gives us an upper bound on this term. So we have C times alpha k squared times this gradient norm. Okay. Okay. Some unknown capital C. Okay, so is everyone with me so far? Okay, so here's where we actually get to think about this. So remember that my goal is to start at this level of cost and decrease the cost. So we want the left side to be smaller than this. So that means that everything that comes after it should be negative. If I make that stuff in the red box negative, it means my new cost is smaller than my current cost. And when we look at the two terms here, one of them is negative, but the other one is positive. And that means, or it could be positive at least. It's upper bounded by something that could be positive. So this term is helpful. This is helping to decrease our cost. This is harmful. This may be increasing our cost. We need that together. Those two things are negative. They both involve the norm squared. So really, it's about minus alpha k plus c alpha k squared. We want the sum of those two things to be negative. So let's look at the very specific value that balances the size of those two. Can anyone see what is the value of alpha k for which those two things cancel out? What's that?
Should be less than 1.
So when it's 1 over c, right?
Yeah,
when it's 1 over c, then this is minus 1 over c, and this is positive 1 over c, and they cancel. So that's sort of, if alpha k is 1 over c, I make no progress. So that's sort of just on the edge of where this is going to work. If I actually want to make progress, I want to make alpha k smaller than 1 over c, because when that's smaller than 1 over c, then this side is, well, this negative number overwhelms this positive number. Okay. So here you can see, this is why we need a small step size. If the step size is small enough, gradient descent will make progress in minimizing this function. Yes?
Can you repeat where the C came from?
Yes, that's a great question. So the value of C really depends on the function that we're minimizing. So if I'm minimizing this function, this is in one dimension, and this is where I am at omega k, it's really sort of about, there's a linear approximation, and then there's an error. And it really depends on the shape of the function at that point. It's something that changes every time we take a gradient step. And so we don't really know what it is. Now, for some classes of functions, you can say, okay, at most C, anywhere I go will be a certain value. And in that case, you can actually say, before you even start running the algorithm, this is my maximum step size. I'm going to make sure to use something smaller than that. In this analysis, we don't actually know what C is, but we're just saying, no matter what C is, there's always a step size that is smaller than it. So there's always some step size where I can make progress. The exact choice of the step size is a great question, and we'll see the effect of it, and we'll actually derive an algorithm, not today, but next week, that automatically adjusts the step size as we descend so that we always make progress. But the basic gradient descent algorithm, the simplest version might just use a constant alpha k for all k. You just set it as a small number. But yeah, that's something we need to discuss more. But the overall thing we've done here is we figured out that this idea works if we choose a small enough positive step size. Then, yes, we will make progress with this algorithm. This will actually work.
And also, from the big O of that term,
Mm-hmm.
we wrote C times alpha square. So, how did we bring the C over there?
So that, like, big O of something means that this is upper bounded by C times that something. That's all.
So, if the value of alpha k is between 0 and 1, this should always work.
Well, okay, we need alpha k to be between 0 and 1 over c to make progress. If alpha k is exactly 1 over c, then these two terms could cancel and we might make no progress.
Yeah.
And if alpha k is greater than 1 over c, that means that actually we could make negative progress.
Yeah.
So, okay, good. Any questions? Okay, excellent. All right, let's do, maybe just start on one more page. So we now have this algorithm. We want to come back to our original goal of this unit, or maybe one of the goals, which was to optimize this binary logistic regression loss. And so here's the loss function, stated in terms of the score for the ith training sample zi. And if you remember, that is going to be the inner product of this extended feature vector for the ith sample times the vector of weights that we're designing. So what's a little bit complicated is you sort of have like a two-part, we're expressing this in two parts. First, we're saying how does W relate to Z, and then how do the Z's relate to the cost. This is the way it's typically written. You could, of course, plug this in here, but then the expression just gets a little bit more complicated. The efficient solution to this problem is also best thought about in terms of this like two-stage approach. Think of this cost J as a composition of two functions. One of them starts with the W vector and multiplies by this A matrix to get you a Z vector, stage one. Stage two takes that Z vector and splits it into components Zi and processes each one of them independently by some scalar function Ji. So that scalar function, if you look at this, is just this. And then finally, you sum them together. Okay, so at a high level, the first stage is a linear stage taking you linearly from W to Z. What's complicated about that stage is that all these W coefficients get kind of mixed together to make all the Z coefficients. That's what's complicated. What's simple is that it's linear. Then when you think about the second stage, what's complicated about this second stage is that it's nonlinear, but what's simple about it is that it decouples element-wise. Each of the Z's is processed individually. There's no mixing among the Z's. So that is the form of a lot of cost functions in machine learning. It's a composition of a linear function followed by an element-wise nonlinearity. And so that's going to be our approach to make this tractable. We basically want to compute this gradient, right? We want to compute, these are the terms of the gradient vector. How do we compute these? So we're going to use what's called the multivariable chain rule. It's something you've all seen in calculus, but we're going to start using it quite a bit. So it has this form. Sort of makes sense if you look at it. It says the derivative of J with respect to the jth coefficient Wj is going to be the sum over all the samples of the derivative of J with respect to Zi times the derivative of Zi with respect to Wj. Visually, one way you can think about this, maybe, is that you draw a little diagram where you represent Wj by this node. And the effect of that Wj, if I change Wj, in other words, if I change one element in this vector, it has an effect on all the Z's. Right? It changes all the Z's. So you can think about this. These are all your Z terms. And then your final cost J is some processing of all those Z's. And so what the multivariate chain rule says is that when you look at how does Wj affect how does this W affect this big J? You look at the gradient, but you have to look at what happens separately over all those paths. So each one of the terms in the sum is sort of one of the ways that information flows from Wj to this big J. And for each one of these, this is just the standard chain rule that we're used to using. And this just says, do that standard chain rule, but with all the different ways that information can flow from Wj to big J. So just a little bit of intuition as to the form of this. Okay, so any questions on this chain rule here? Okay, like I said, we'll see a lot of it, so if it's not making sense yet, that's absolutely fine. So now we got to figure out what are these two terms. Neither are terribly difficult, so let's first look at dj dzi. So So if I look at dj dzi, only one term in the sum matters. It's the ith term. So I can look at the derivative of this with respect to zi. And to do that, remember that the log is 1 over, when you take the gradient of the log, you get 1 over the result. And then by the chain rule, you have to further differentiate what's inside that log, which gives you EZI. And then you differentiate the second term with respect to ZI, and you just get YI. Okay, so this is this. And then what about this one? So for this one, we would like to, let's see. Okay, I didn't write it here. We would like to write it, again, in terms of scalars. So if I say, how can I write an expression for, actually, maybe let me do it for here. I look at the ith term here. This is going to be a sum over different indices j of a, I, j, w, j. So this is just another way of writing this matrix vector multiply. And from this expression, it's very clear what this derivative is. It's just aij. Okay. So we have basically the ingredients of what we need for the gradient. To make this efficient in terms of implementation, we want to write things back in terms of matrices and vectors. We'll do that next week. Midterm is Friday. If you guys have any last questions about the midterm, do you want to ask them now, or? Yes?
We could write our one-sided sheet notability, right?
Yeah, you can write it on a tablet electronically and print it out. That's fine. Okay, any other questions? Great. See you guys on Friday.